Donc en fait, chacun des filaments jaunes, l'air de rien, éclaire certains de ces LED.
Oui, mais les filaments jaunes, ils sont
Jaune,
connectés.
hein, jaune, ouais. Donc Philippe, nous écoutons tes suppositions sur les composants et sur l'utilité de l'agencement.
L'éventuelle utilisation.
Hello, bonjour. I am Yann Guidon and I'm sorry for my funny voice, I got a cold. I made this video to present and explain the project titled Numitron hexadecimal display module, which I have submitted among many other projects to the 2018 Hackaday Prize. I'm sorry I have not found a fancy catchy name this time, but don't let that distract you. I could describe this project as a sort of Russian lipogram, but instead of avoiding a particular letter, I avoid transistors. So this project uses only Russian D9K germanium point contact diodes, Russian IV9 numitron tubes, and Russian Res15 miniature low voltage relays. Okay, it's not the sort of feel-good project that will make the world a much happier place tomorrow. I'm not sowing hope, I'm just doing some fundamental research and I study very basic needs. Here the need is to display numbers without transistors, as if the bipolar transistor was never discovered. It's a sort of steampunk that can be called electropunk or neo-vintage. Indeed, I am one of many amateur CPU designers on Hackaday and other sites, and my entries this year and in the past have proven my strong interest in CPU architecture and building. 2 years ago I started playing with obsolete and even antique technologies. I tried germanium transistors, but they are still too advanced. Then I discovered tiny Soviet relays on eBay and I became immediately hooked. They are not perfect, but they are cheap, cute, and good enough. I tried to make a small project with them, but the urge to make a relay-based Turing-complete machine was too strong. Of course, these old Soviet parts are both exotic and vintage, and I managed to import a significant quantity from Ukraine, but at only one visible side of the project. The real problem I wanted to study is how could the Russians or even the Germans even manage to build calculating machines with such a lousy technology? How did our grandfathers do anything? What would I do if I was a Soviet citizen tasked with making useful stuff using these anachronic parts? How could I design something around all those idiosyncrasies? I started to design circuits using these antiquated parts, mostly out of the Red Army's surplus stocks available on eBay. I am currently developing a new minimalist processor architecture called Y. It must be generic enough to work with any electronic technology, like relays, discrete transistors, FPGA, integrated circuits. But whatever the technology you choose, whenever you start to put circuits together, you need ways to input and output data. Any test requires injection of value and readout on a suitable display. So actually I'm trying to do what Artem currently does with VFT and microcontrollers, but without transistors. His video clearly shows his display, and this illustrates that a numeric visualization is essential during development. It's a matter of design for test. You need something in and something out to debug a circuit. And unlike Artem, for me it's out of question to use an Arduino or Raspberry Pi since our grandfathers didn't even have them. Displaying values with modern technologies wouldn't be fair for this project, it would be like cheating. And after the design phase, the displays will stay in place to show the current values and state of the registers and buses of the whole computer. So it must remain in the theme. Displaying numbers is an inherent requirement when you design a new computer from scratch. I have evaluated several techniques. Straight binary display with one light dot per bit like this IBM front panel simply is not acceptable or user-friendly. Our brain loves digits, not bits. We're in the 21st century, damn it. So the next logical thing to try is galvanometers, where the needle indicates a value which is proportional to the current. After all, a 4-bit R2R DAC is straightforward and requires only 4 relays. Well, in theory. In practice, the display is slow and imprecise. It's much harder to calibrate than I thought. It's cheap but not linear or reliable. A digital computer needs a full digital circuit, even though it's more expensive. There are various vintage and neo-vintage display types, such as the Nixie tubes and the VFD tubes, as used for electropunk clocks, for example. Mark Miller created a simpler and more scalable version with neon indicators. The problem is high voltages. I want to power the whole computer with low voltage for safety and simplicity. I suppose and expect that kids will touch them. The solution comes again from eBay, where I have found the IV9, a Russian clone of RCA's classic numitron. This is a 7-segments display introduced in the 1970s, but it's also a low-voltage light bulb with 8 filaments, including one for the decimal point, which I ignore. Each filament represents one segment that glows at about 2 volts and less than 20 milliamperes, which is compatible with my low-voltage relays and low-voltage glue junction. It's safe, it looks very cool, or would I say warm. It doesn't burn to the touch, and I managed to import enough of them to display the whole state of my 16-bit processor. Of course, it's not so simple. Scalability and price were quickly estimated, and I would need too many parts. The display would occupy a significant volume, use too many relays from the stock, and these relays wouldn't be used for the processor's core. So this is where it becomes really interesting. I needed to keep the parts count as low as possible. I needed to optimize the circuit. So let's start with, how would you design a 7-segments decoder out of relays? First, you have to demultiplex the input code with a binary tree of SPDT relays. For an octal display, you need 7 relays and 15 for an hexadecimal display. An octal display module is cheaper, but you need more of them, and the system-wide cost is almost the same. So I have chosen a hexadecimal display because fewer modules are required. But the number of relays must also be reduced to make the project possible. And I realized that unlike Nixies or VFD tubes, numitrons are not polarized. The current can flow in both directions in the filament. This direction could be used to reduce the size of the binary tree by swapping the polarity of the power supply rails. So with only one more relay that selects between the positive and the negative rail, I could save 8 relays. The problem is now how to design a diode ROM that works in both directions. Here I use old D9K germanium point contact diodes with quite low forward voltages, so running the array backwards creates all kinds of loops and shadow segments light up. The first big trick of this project was to design a diode ROM that works in both directions. Your typical diode ROM lets current flow only in one direction, but I added a row of diodes to prevent loops from turning unwanted segments on. Of course, there are still loops, and germanium diodes are pretty leaky, but the current and voltage at the filament is much too weak to make it glow. So yes, I solved this issue! But it's not over. Now I have a binary tree with only 7 relays, plus 1 to change the polarity. 8 relays is much better than 15, but driving them all creates a new problem. One requirement of the module is to provide identical impedances for each of the 4 digital inputs. But one of the bits will drive 2 relay coils and another will drive 4 of them. 2 more relays must be added as buffer, so the total count is now 10. Without the bidirectional diode ROM explained before, there would be 18 relays, which is not economically feasible. One buffer must drive twice as many coils as the other, but I found another trick, which is called balanced binary tree with balance control. Oh, that's a name. This trick swaps some control signals to create two strings of coils of equal length. A fortunate coincidence makes this trick even better. 3 coils in series can be driven by the 6.6 volts supply rail that powers the rest of the relay computer. These permutation tricks that balance the length of the control signals are the subject of upcoming publications, as they have a very wide application range and they could even speed up integrated circuits. So I made a first working prototype. But now I had to optimize the diode ROM. The new row of 14 diodes increases the bill of material and the costs. The third and last trick is a certain kind of logic minimization, but adapted to SPDT relays. I give you an example. Take the digits 0 and 1. In both digits, the segments B and C are on. Segments A, D, E and F are on only when the digit is 0. This means that it is possible to share diodes and more optimizations are possible. I wrote a little program to evaluate which permutations of the input bits would provide the most savings. The logs detail how I reduced the diodes count of the ROM from 77 to only 45. Even with the additional 14 diodes for the bidirectional trick, the total is only 59. So I saved 18 diodes, which makes the module smaller and cheaper. Well, it's possible to have only 35 diodes with negative logic, but this would require 7 inverters and the cost would increase. I made another prototype to validate this circuit on prototype solder boards. I built this one especially to show it off and confuse hackers. When the circuit is off, you cannot easily guess what it does, and many people were puzzled both by the unusual circuit and by the practically unknown Russian parts. Les LED nous montrent comment fonctionne la matrice. Parce que au lieu d'utiliser que des lignes et des colonnes, j'utilise des demi-lignes et des quarts de ligne parce que il y a certains codes qui sont redondants. Donc ça évite de mettre trop de diodes, vu que ça coûte cher hein, ces trucs-là. Donc nous avons bien 1, 2, 4, 8 et toutes les combinaisons. Donc nous avons 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E et F. Et donc, on voit par où passent les signaux.
Non, moi, ce qui continue de m'intriguer, c'est ça.
Ces indications-là.
Ouais. Parce que là, ça part d'ici, en fait. A, B, C, D, et puis là, ça part de la 0.
En fait, ça part des boutons.
Bon, ça part des boutons.
Ah oui, forcément.
Oui, parce que ça suit. Oui.
Voilà.
Le bleu, il est là. Le bleu,
donc ça va des boutons vers les espèces de canettes, là. Mm. Et ensuite, les canettes sont reliées au LED.
Là. Les résistances qui sont ici, ben, il y a surtout la rouge et la noire. Ah, je l'avais oublié, la noire, tiens, qui est reliée là, à la 1. Ceux-là, je vois pas de fil comme la rouge, par exemple, qui est reliée à celui-là. Où est-ce qu'il est, la 1 Là, il est... Non, la 1, il va à lui, là, apparemment. Donc, c'est deux là. Donc, je pourrais redessiner un circuit à côté, mais malgré tout, le seul truc que je peux juste te dire, c'est qu'avec de l'alimentation, ça s'allume. Ça, je savais pas que ça s'allumait.
Bah maintenant, tu le sais.
Ça, ma foi, je sais toujours pas ce que c'est, finalement. Clairement.
C'est un truc tout con.
Oui, mais je ne sais pas ce que c'est. Et je ne sais toujours pas si c'est un jeu. C'est ça qui me titille. Qu'est-ce qui se passe quand on appuie là-dessus?
Ça m'étonnerait que ce soit des LED. Si c'est des phototransistors.
Dans un montage, c'est toujours la faute au transistor, c'est sûr.
Ça
Par rapport à d'autres, c'est le seul qui retourne au moins. Hein.
Moi j'ai retourné. Il y a des grosses bobines là, à ton avis c'est quoi?
J'allais dire des capas, mais je me trompe peut-être, c'est peut-être des relais. Il y a combien de pattes là-dessus? Il y a 5 pattes.
Ouais.
C'est bien.
Bon.
Donc 5 pattes, c'est effectivement des inverseurs. Il n'y a que 2 fils d'alimentation et des poussoirs.
Ouais. C'est clair en tout cas.
Ben, j'appuie. Oh putain, une
Tu l'as
calculette.
branché ou pas?
Non, ça peut pas être une calculette. En tout cas, l'affichage et ça a un lien. 1, 2, 4, 8, donc c'est du binaire.
Ah bah ouais.
Donc, je sais pas, moi, j'appuie sur 4, 2 et 2, et je me retrouve avec un 6 affiché là.
4, 2 et 2
4 et 2.
Ah oui.
Oui.
Et j'ai un 6 affiché là.
Il y en a beaucoup qui t'ont dit ça?
Gratifié. Ouais, 1 point.